Welcome to the Valve Studio. It's Sunday afternoon here in Colorado. It's a beautiful day, and I'm in here tweaking with tubes. That's okay. Let me go over a few things first, and we'll get to today. We'll get to today's topic. I've had a pretty hectic schedule for the last 3 weeks. That's why I haven't posted anything. Let me see. About 3 weeks ago, I went to an estate sale, and I bought this baby back here. This is a Marshall JCM 800 by 1984 version with a 412 cabinet. This thing is an amplifier I thought I would never be able to own. I saw it and immediately bought it. I bought a bunch of other stuff as well. This thing is awesome. It's just absolutely awesome. But it does have a few problems. We're not going into that just yet. In fact, I am not intentionally going to open that up until I get a lot of my other stuff done here on the bench. Got a lot of commitments to finishing off this Mectron amp. I will go over a couple other things. I think 2 weeks ago I was at a garage sale and I got this. I've had on my list to buy for quite some time is some rivets for my rivet gun so that I could put terminal strips into amplifiers. But I ended up finding this whole thing here. This is a whole cabinet full of different rivets of different sizes and a much better rivet gun than I had. So that's a great thing. And on eBay, something came over in one of my searches. This thing here, this is a Acrosound ultralinear transformer at the TO305. One of my purchases quite some time ago is a mono amp that has this transformer in it. So now I have two of these output transformers. I'm going to make a couple of mono blocks for like a 6v6 with these two transformers. So this all came in, and there's a bunch of other stuff in here as well. But that's not what I'm going to cover today. Let's go ahead and move right on into that. I've been doing a lot of reading on transformers, transformer design, transformer windings in the evenings, right before I go to bed. I've been reading some really old books for that. And there's a lot of equations for this. A good transformer design, you might want to have like 20 equations all working together to give you things like flux density, permeability, winding ratios, impedance matching, plate resistance, power dissipation, leakage capacitance and leakage inductance, and or parasitic capacitance. So all those equations are all kind of intertwined together, and you have to kind of tweak them all. And these books that I've been reading in the 40s and 50s, or basically in general of transformer design, you pick a bunch of stuff that and then you iterate to the answer to see if that's what you want. And if it's not quite what you want, a lot of times the frequency response isn't quite right, or your design won't fit in the window of the core, those type of things, or you want to pick larger windings to lower the power dissipation. There's a lot of trade-offs in the transformer design. And it's an iterative process because they're so intertwined, these equations. So I'm going to show you today is my initial work on trying to dramatically simplify the iterative process. And let's go ahead and get started with that. A little bit of intro. When I was in undergraduate school, I bought a Macintosh Plus in 1985. And I ended up getting from some friends of mine a program called TK Solver, and TK Solver was this really, really simple program for the Mac that would allow you to write a series of equations, simultaneous equations, in any form you wanted to write them in. So you didn't have to rearrange any of the equations. You could write the right-hand side and the left-hand side in any form you wanted to. And then you would type in the values that you knew, the numerical values you knew, and then you would type in some guesses for the initial guesses for the iteration to take place. And from an analog design perspective, there's no tool exists today like TK Solver. A lot of people say, well, you could use MathCAD, you could use Excel, you can use Mathematica or a Math Lab or Octave or all these different types of programs. Nothing is as simple as TK Solver. Now, at some point, people were making Mac emulators for Linux, and I miraculously had a Mac image from a long ago, and I was able to extract out the TK Solver application, and I was able to put it on one of these Mac emulators. I'm going to show you that in a few minutes, and I'll show you how simple it was. But now I've been trying to figure out how to use updated open source programs to give you the same type of functionality as TK Solver. And I don't know, at some point about 4 months ago, I started looking at using NumPy and SciPy, and that combined with Jupyter Notebooks to give you the same kind of functionality. I got something else cooking today. It's even simpler than what I was doing before. And then in the next segment after this, I'll make it even simpler than that. So let's get started. I'll go ahead and show you a few equations that are how you actually enter them into this thing called sympy, which is a symbolic interpreter for Python. And we're going to use it to get us the right form of our simultaneous equations. And then we're going to use its numerical solver to go through and take the numerical values that we know and iterate to the values that we want to find. So it really closely emulates what TK Solver does. The interface isn't quite as pretty, but we'll handle that in future segments. So let's get started. All right, so let me fire up this Mac emulator. It's called MiniMac, and you'll see how fast this thing actually boots. It's going to come up in this window. So this is running, what's this running? System 7? System 6. TK Solver was originally available long ago from a company called Software Arts. That since has been taken over by somebody else. I'll have those notes in the show notes. So basically what you have is a variable sheet and a rule sheet. You type your equations in down here. So what we'll start with is a simple voltage divider. And we'll say that with two resistors. So we got I equals Vn divided by R1 plus R2. Let's type this a little better. Vn divided by R1 plus R2. What this does is it goes and parses this line out and puts our variables up here. And then V out is equal to R2 times I. So these are our 5 variables in 2 equations and 2 unknowns. So we need to make 3. We need to come up with 3 of these. So let's say our Vn to start out with is 10. We want our V out to be 7.5. And we pick one of these resistors to be, let's say, 2000. And if you hit this exclamation point, it's going to solve this equation, but it can't get started because it's an iterative solver. So you need to give it an initial seed on one of these values over here. So we'll say that R2 is equal to 1000. This is just initial guess to get the iteration started. Okay, so now we got our I is 0.00125. This is 1.25 milliohms. Or milliamps, and R is 6,000 ohms. So this is completely freeform. So let's say that we wanted, say we didn't know what V out was, but we knew what R1 and R2 were. So let's link this like 333, and we hit this here, and it could do a direct solve on this thing. So it figured out I at 4.3 milliamps, and V out is 1.43. Yeah, so you could basically pick any of the three variables here that you want, and it will set the other 2. So we can completely change all this. Let's make that 100. And so now we got two unknowns here, so we can do that. We want 2 milliamps out. So V out is that. Let's make this a little bit bigger. Let's make this 100,000. Now we got a negative value here, so we got something that's a little bit wrong. That's a little bit high. Okay, there we go. So you can kind of get the gist of it. It's super simple to do. Use this thing. It's a free form thing, so you don't have to. You can rearrange your equations down here any way you want to. Let's say you wanted to move this over here. These don't even as long as they're correct. Oops, there's no copy and paste in this thing. So we can come over and say I1 times R1 plus R2 is equal to Vn. Okay, so we got the same the things up here. So we'll go back to our original settings. This was our guess, and V out was 7.5. And this is, let's get rid of that value there. Okay, so now we're back. We've rearranged equations down here. We get the same results up here. All right, so this is TK Solver for doing analog circuit design. This thing is great. There's nothing like this. And trust me, I've been looking ever since I became a Unix guy, maybe about 15 years ago. I've been looking for an equivalent to TK Solver, and it just doesn't exist. Not that's super simple like this. You get the same kind of functionality in a nonlinear solver, but it's much more complicated to get set up. This is a really simplistic spreadsheet-like interface for your variables input, and the rules can be free form without doing any kind of rearranging of the right or left-hand side of your equations. All right, let's go on to show what I have using sympy. Here I have Jupyter running locally, and I'm going to create a new Python 2 notebook. And we are going to use sympy, and let's put in some. Let's full screen this here. Let's put in a markdown cell right here, and here's the link to the solvers that showed me how to do this. Okay, we're in the code section. So I want to import a bunch of stuff. I'm copying and pasting it from a different place. What I need is a symbol in solve and this thing called EQ, which is equality. And I'm going to import a bunch of other stuff as well. So let me just paste in some code from what I was doing before. We're going to use the display module in IPython. We are going to init this printing thing. This one's actually pretty interesting. It tells you to use LaTeX, add math jacks. That's going to make it so that we can print in LaTeX format. The first thing we got to do down here after this cell is we have to create these things called symbols. Now, sympy is a symbolic interpreter, so you can put in a bunch of equations and it will solve the equations symbolically, which means they don't need values, numerical values in them. But in order for that to work right, we want to create some symbols for the variables that we're going to use. So I'm going to use this thing here called the symbol class, and I'm going to create a couple of these. I'm just typing these in by hand. I'll paste these next to these in a minute because I'm not typing too well this evening. Okay, so you create all the symbols for your functions. Let me paste in some other ones here. And actually, I'm going to put an underscore sign here, right here. I'll tell you why we did this in a minute. So here's the 5 symbols using, and let me see if I can bring up that. I got a lot of things here going. Let me see. No, not TK. Where was that? There it is. Here's the thing we're trying to emulate. This is the TK solver page for the voltage divider. All right, so now I'm going to write a couple of equations. The way you do that is I'm going to say E1 equals EQ, and you put in the left-hand side first. So what was my first equation? My first equation was the I equation. So I, comma, Vn R1 plus R2. All right, so that's the first equation. Equation 2 is EQ V out I little I times R2. All right, and we can use that display function I imported above to look at my E1 and E2 equations. So let's go ahead and run this. So here's the LaTeX formatted version of our two equations. These two, this underscore symbol here actually makes these subscripted. Like if I change, let me go here and change. I'll take this one out and I'll rerun this. You can see that this one didn't get subscripted. So if this actually accepts LaTeX formatting up here as well. All right. So that's we just have our equations in. Now here's remember on over here on I keep losing my thing. Okay, over here we need to set some of these values. So let's set Vn to 10, R1 to 2000, and V out to 7.5. Let's do that down here. So we're going to say V out equals 10. R1, what was that equal? 2000. And V out, no, Vn was 10. Vn is 10, V out was 7.5. All right, now we're going to, this is actually kind of sloppy, but I'm going to paste these in again down here. And so you'll see these are the symbolic equations, and then these are the ones that are that it's actually going to solve. Now this, you could just do straight substitution for this if you wanted to, but you'll see here in a few minutes why we don't want to do that. Not really on this simple voltage divider. This one you can pretty much do in your head. But all right, so we're going to use this thing called nsolve. This is the numeric solver. That's part of sympy. So the first thing you do is you put your array of equations in, and then you put in the variables that you're going to iterate on. So we want to iterate on what R2 and what. Let me put a thing up here. I can't see what I was doing. So we want R2 and I, right? We want it to find R2 and I. We've given it everything else. And nsolve requires that you put in an initial guess for these two variables, R2 and I. So we're going to put in 1,000, and we'll put in a 0.01. And it's done. No, it's not done. We have, this thing doesn't, we have it says here, try a different starting point. Okay, let's try 10,000. All right, there we go. We didn't get an error, didn't throw us, so that's good. So we'll do a print, couple of print statements down here, and we'll say that what R2 equals. Let me see. This R2 is going to come out in A2 over here. So it's A1, I'm sorry. And I is going to come out in the variable underscore A2. There's nothing fancy. I just put this underscore in here to not have a name clash with if we used A1 up here. So we run this again, and we see that R2 is 6,000 and I is 1.25 milliamps, which is what we got before. Okay, we got 1.25 and 6,000. Okay, there you have it. So you could pretty much put anything in these equations you want. I'll come up with a little more interesting thing to solve for in my next example. All right, let's pick a little more complicated example of triode biasing for not grid biasing, but cathode biasing. It involves a cathode bias resistor, so the quiescent plate current actually sets the cathode voltage above the plate voltage. So we introduce a negative potential across here. So our grid cathode voltage is set by the current through this resistor here. And we're going to use the modeling from the Child-Langmuir equations. If you want to look at a video that I posted about the triode modeling notebook, you can come over and look at this one here. This is on my GitHub page. This is a complete example of all the biasing that I did using load lines and data extraction, but we don't need to talk about that today. No, I don't know if I can go back here. Let's put that away. Where'd we go? Okay, so here's our circuit. So what we're going to do is type in all the equations that we know about this, and we're going to use the same kind of methodology where we put in the values that we do know, and we're going to have sympy iterate to the answers that for the other variables that we do not know. The Child-Langmuir equation is shown here. We don't need to go into that other than the fact that now from a symbol perspective we have 1, 2, 3, 4, 5 symbols just for the anode current or the plate current. So let's start off by defining some voltages that we have. First one's going to be, our first equation is VA, which is the anode voltage right here, is going to be the battery voltage minus the voltage drop across the load resistor. And our next equation is the Langmuir equation for the anode current. I got it here. I'm pasting these in from another window just to make this a little bit more bearable. The cathode voltage, VK, is right here, and we're just, the anode current comes down, creates a voltage drop across this resistor here. Now, the grid to cathode voltage is going to be a negative perspective because this is zero. This is zero because no current's flowing out the grid at the time. So this resistor here, doesn't matter what it is. So this is a zero potential. And the next equation, we want to calculate VAK. So we're going to take the battery voltage minus this drop. Well, we already know this voltage in this one, so we just do a simple subtraction. And one last equation that kind of binds this solution together is the power dissipation, which is the anode current times VAK, which is the voltage across the actual tube itself. Here's our 6 equations. In one respect, they're simple, but the Child-Langmuir equation right here makes it actually pretty complicated to solve symbolically. So we're not going to do that. We're going to put this into insolve like we did before with the voltage divider. Let's see what we get. Remember, we have to create the symbols for these, so I'm going to paste in all the symbols for all these equations. So here's all the equations up here. And let's go ahead and hit the display down here. So we're going to display these values. Let's display these equations. Okay, so here's all of our equations we're going to solve. We're going to put these back, all these 6 equations in the solver. But we do know some of these values. You know, like I said, we know the battery voltage. And we know, what else do we know? We'll put some limits down. But basically with a solver, the point of all this is we could go in and pick whichever variables we don't know, and we can pick what we know and what we don't know, and we pick what we know, and we can solve for what we don't know. There we go. All right, let me put in what we do know. We want the battery voltage to be 250, and we want the anode voltage to be right in the middle of that. So we want this voltage right here at when no AC is supplied. We want this voltage to be exactly halfway through the middle of that. That's going to give us the widest voltage swing. K here is the one of these constants that I determined up in this modeling notebook. I just copied it right out, as well as dA. I did this from I modeled this and actually numerically determined what those are from curve fitting. And the last one I threw in down at the bottom is a power dissipation. Now this biasing doesn't look at any kind of gains or anything. I figured let's just keep it as a kind of complicated, but not really that difficult to express, because we have 6 equations and 6 unknowns as it is. If we want to really look and do a full design where we look at the AC components and the DC components at the same time, and we can incorporate in the frequency response, that we can also do that with this. But that would, that would give us another probably 4 or 5 equations down here. So let's just, 6 equations and 6 unknowns is complicated enough for us for today. All right, so let's evaluate this cell. Okay, now when we did it this time, we actually had some numerical values. So sympy actually did some substitutions into all of our equations, and this is what we're actually going to solve for. Here's our series of equations. So let's write our n squared, our n solve function, and we're just going to put all of it into an array called answers. And this is n solve. And the first thing we want to do is we're going to pass in all of our equations that we have, and then we're going to start looking for the values that we don't know. So what's the first one we don't know? If we kind of just look at what we have here, there's the ones we do know. So we don't know R load, so let's put that in there. Next one down is going to be RK. We don't know RK. And we don't know that resistor. We don't know this one. So let's put in RK. And we don't know IA, which is the anode voltage here. Don't know that. What else we don't know? We don't know VAK. We don't know that one or this one. So put that down there. What else don't we know? We don't know VK, which is this value here. VK. We know VA. The last one is we don't know VGK. Okay. So these are our equations. These are the equations. These are the symbols it's going to solve for, and I'll put in our initial guess. So for R load, let's say it's 100K. The cathode resistor, let's say it's going to be 100. Our current, let's say 1 milliamp. VAK, let's set that to 100. We don't know what that's going to be. And VK, which is the voltage here, let's set it to 1 or something like that. It just needs to be defined to something or other. Which means the other voltage, VGK, which is the same voltage because this is 0, is minus 1. All right, let's solve here. And, we didn't get an error, so that's good. So let's print this out. Let's run this cell again. And here are our values. Well, how about that? What do we get out of here? We got R load is R load's the first one to come out. This is 62.4. RK is 55.9. We got, this is IA right here. That's 2 milliamps. VAK, which is this voltage here, is 124.9. VK and VGK are the same at 111 millivolts. All right. Well, that was fast, wasn't it? So it solved all these 6 equations to 6 unknowns, just almost right immediately. Let's go over and look. I did type these equations into TK Solver. Let's go over and find that window. So I have the exact same equations in here. Now I've done it. It's exact same equations in here, and I ran the simulation as well. We can, I can just do that right here. Just put in 100,000 and run this again. We need to give it some more guesses here. This one was about 100. Oh, that was a guess. Man, what's going on? I was grabbing my mouse. Let's see what this is going to happen here. There we go. So we iterated on the answer down here. We have 62.4. Man, what is going on here? It's grabbing my mouse. There we go. Let's do that. All right. Can't go over that across the front of that window. IA is 2 milliamps. That 55. RK is 55. VAK. VAK, yeah, that is the 124, which is right here. VAK. And we got VK, which is the cathode voltage, is this 0.111, and we get minus there. So we get the same answer out of TK Solver as we do out of sympy. So what we can do is, at this point, we can come in and if we want to, change some things, like we want a specific load resistor, we could take this one out and look at the power dissipation changes. We can, you can basically you can put in the things that you want as part of your design criteria and have this thing iterate out all the other stuff. This was a pretty simple example. It did involve a little bit of complexity because this equation here is not kind of easy to solve symbolically. But if we want to really tweak our design, we can just go ahead and pull different values out here, set them up here, and put the values that we don't know down here and see what we get. What I'm going to use this for in the future is for transformers, because what's going to happen in a transformer design is this series of equations here, there might be 20 of them, and it's going to get fairly complicated to do that. Now, I could just use TK Solver, but then that doesn't help you out because you don't have TK Solver. But we do have sympy, so we're going to take the same approach that we did here and apply it to transformers and get a really good tool to actually do transformer design, because there's a lot of intertwining of equations at that level as well. I am working on a little something different to get my interface into the sympy to look a lot more like this, where it's kind of a spreadsheet metaphor. Instead of having to type out all this stuff, you'll actually just type it in just like you do over here. And I do have some of that working, but I'm not going to show you that today. I have a little bit more code and some testing to do, but I want to get down to this level of simplicity, but use this engine's level of complexity. Create a notebook. We're going to tie it to a Google Doc so that you can save your designs and just run my tool with your designs and you save it in your own Google Docs. It sounds pretty complicated, but it's going to give you a really powerful tool to actually do nonlinear solving, numerical solving, for complex systems of equations, which is what we need when we do these tube amplifier designs. I'm going to wrap it up for today. It's been pretty long. Thanks for watching if you made it this far. This is the Val Studio.